Cockcroft-Walton experiment. So Walton was Irish, which is partly why this is on the syllabus. All right, let's look at the syllabus first of all. So we're looking at the Cockcroft-Walton experiment. And if we look at the right-hand side, the STS, the Science, Technology and Society section, and the reason it's important is it's the first artificial splitting of the nucleus. It's the first transmutation using artificially accelerated particles. And they won the Nobel Prize in Physics. Transmutation means you have two particles, they collide, and then after collision you get out two completely different particles. Also, it is the first using artificially accelerated particles, so they created the means by which to accelerate the proton. As far as I know, Rutherford did another transmutation experiment using artificially particles, but they weren't artificially accelerated. Okay, back to the depth of treatment section. It says the proton energy is approximately 1 mega electron volt going into the collision, and then we need to have a look at the experiment. Now, if we jump down to number 3 there, splitting the nucleus essentially, what you have is the reaction equation: 1 proton plus a lithium nucleus, and it decays or creates or transmutes into 2 helium nuclei plus energy. And below it, we have the input energy of 1 mega electron volts, so the proton is accelerated to a velocity that gives it a total energy of 1 mega electron volt. But afterwards, the combined energy of the 2 helium nuclei is 17.3 mega electron volts. So there's an energy gain, and the energy gain is caused by a decrease in mass between the products and the reaction, or the reactants even. And that's consistent with E equals mc squared. So let's have a look at just the experiment first of all. There's your diagram, step by step. Protons are produced in the hydrogen discharge tube and they're injected into the evacuated tube. They're accelerated down by the high potential difference of 0, 200 and 400 kilovolts. Those values vary from book to book, but we're going to stick with 0, 200 and 400 kilovolts. Remember that potential difference is the difference in potential between 2 points, so you need a plate that's got a large charge density on it and a plate that has a smaller charge density on it. In this case, the smallest charge density you can have is 0. So to get the 400 kilovolts, it's connected across a plate that's got 400 kilovolts of potential on it and a plate that's got 0 potential on it. And then the 200 kilovolts connected across a plate with 200 kilovolts potential on it and 0 potential on the other plate. Okay, so the reason they use protons is because a proton is a charged particle, and a charged particle can be accelerated in an electric field. Like a neutron wouldn't work here because it can't be accelerated. The tube is evacuated because if there are particles in there, they'll just get in the way of the protons being accelerated, and as a result then it will make the protons hit off those particles and they may rebound anywhere. Eventually what happens is the proton strikes off the lithium plate at a 45-degree angle. So the lithium plate is at an angle there, and what happens is transmutation occurs, 2 alpha particles are produced, they travel in opposite directions with the same velocity. So their momentum are equal but opposite. So the alpha particles, after transmutation occurs, there is no net momentum. And before the protons collide off the lithium target, there is no momentum in the horizontal direction. So just lengthways rather than vertically up and down. So no momentum beforehand, no net momentum afterwards horizontally. Okay, the alpha particles collide off zinc sulfide screens. As a result, we get scintillations or little sparks of light, and those sparks of light can be seen on the microscope. And those sparks of light are of an energy roughly about 13.6 mega electron volts when you account for both of them. Remember, there's only 1 mega electron volt goes in to the proton to cause it to accelerate, and we get much more energy out, which means that some of the mass has to have been converted to energy. Okay, so pause the video and you might answer those questions, or see can you answer them. How are the protons accelerated? How are the alpha particles detected? Why can alpha particles be accelerated but neutrons not? Most of the accelerated protons do not split a lithium nucleus. Explain why. Outline the Cockcroft-Walton experiment. Draw a labeled diagram. Write a nuclear equation. Give 2 advantages of circular over linear. And explain why new particles are produced. The last one you shouldn't be able to do, but here are the answers anyway. Okay, moving forward. So this is what we've done. We've had a look at 2 in its entirety. The only thing we're missing there is the calculations, and I'm going to get you to do those calculations. So it's an E equals mc squared calculation. The formula is on the second column under number 3. H is 1,1H, it's a proton, plus 7,3Li, which is a lithium isotope or lithium nucleus. And then that's converted to 4,2He plus 4,2He, 2 alpha particles, and energy. So add up the masses before, add up the masses after, subtract the 2. That'll give you the mass defect, and then convert that mass defect to energy using E equals mc squared. Finally, I'd like you to convert it to electron volts, and to do that you would divide the energy in joules by the charge on the electron, approximately 1.602 by 10 to the minus 19 coulombs. And that's it.